improve an existing software system using evolution. And I'd just like to tell you a little bit about that and my approach to it. So there's this idea of a Pareto program surface, which I want to introduce to you. So what is a Pareto program surface? Well, this is covered in an ASE keynote paper, because it's got a bit of a mouthful of a name. But if you just type Gizmo with an E, it should come up. And the idea is that we could split software requirements into two different categories. There are the functional and the non-functional requirements. And if we toss functional requirements into a typical Dilbert cube farm, we train software engineers to deal with this all the time, and they're pretty good at dealing with a fairly arbitrary number of functional requirements. This is what most of our programming assignments are about. If we give them lots, maybe some of them pull their hair out, but it's something they can handle. But suppose I now say, as well as that, I want you to reduce the amount of dynamic memory you consume. That's not something that all of our programmers are necessarily good at. I thought you liked the graphics. And suppose we actually said, well, I don't want you just to reduce the amount of dynamic memory consumed, but I also want you to reduce the execution time and the footprint size of your system. Well, I don't know many programmers who can deal with 3 non-functional requirements at once. And actually, in most systems these days, particularly those ones which execute on these kinds of devices, you've got at least 5. You've got those 3, plus reduce the battery consumption and reduce the draw on bandwidth. Now, I don't know any programmers in the world who are capable of optimizing simultaneously 5 non-functional properties. The question, and also they don't just have to do that, they have to do it for multiple versions of the system on different platforms, each of which might be run on different devices, and these objectives are all conflicting. So they might say, well, tell me which one you care about more. And the answer is, well, I care about all of them, I want to see what's possible. So the idea of a Pareto program surface is that only the functional requirements need to be in the domain of the human, and the non-functional requirements should be in the domain of the machine. Just as execution time has been the domain of the compiler optimizer for a lot of time, we want to make these other non-functional requirements into something we could optimize in. But the idea is that whereas a traditional compiler will take one program as source and produce one program as object, we envisage a world in which a compiler will take one program as source and produce multiple, perhaps hundreds of thousands, perhaps even tens of millions of programs as a solution. And of course, the idea is not to deploy all those programs, but to use it to explore the trade-off space. So just as earlier we saw we were trading off cost and value with requirements and test cases, what if we make a Pareto front in which the axes are these non-functional properties, from which we can read off, for example, the footprint size of the program and how much battery it consumes. And each circle is a solution found by machine. So if we change the non-functional properties, we'll get different Pareto fronts, and we'll be able to have different kinds of trade-off. But for any given trade-off of properties, we will have some kind of Pareto front which will tell us what kinds of solutions are possible for this programming problem. So we could start from an existing program, produce this Pareto program surface, which has programs, all of which share the same functionality, but have different non-functional trade-offs, and use this as a design space to just inform the programmer. You know, I didn't know that this was possible. I didn't know you could have a program that could do that particular trade-off. So now I could zoom in on that part of space, generate more solutions, try and find what they all have in common, do all sorts of interesting kinds of programming design level activity. But to be slightly more radical, suppose we turn this into a search space in which the non-functional properties, if you will, are all on one plane, and we actually also bring in the functionality of the system as well, as expressed through the number of failed test cases. So you may say to me, well, I'd only be interested in this solution here, particularly people with a formal verification background would say, well, I'm already rather uncomfortable with the idea that you're testing your software and not proving it correct. But now you're telling me that as well as this solution here, which fails no test cases, you want me to think about these solutions here, which fail test cases. Why on earth would I want to do that? That's kind of insane, right? Is it insane? This formal methods people? I want you to tell me it's insane. I want to convince you it's not, you see. This willing suspension of disbelief. If I put battery life up there, you wouldn't have had a problem at all, right? I mean, if the battery's flat on this, it doesn't matter if you prove the software correct, right? I'm afraid it's useless. In fact, we could argue that the new correctness criterion is having sufficient resources to do computation. But as soon as I put test cases up there, somehow everything changes, right? Like, I would consider all of these solutions as interesting if that's battery life, but if it's failed test cases, somehow we've crossed some kind of Rubicon that people like Dijkstra and Orr sort of set for us as do not cross this line. In fact, get well away from it, right? You know, don't even. So my argument is, actually there are scenarios where this would make sense, and there are scenarios where it wouldn't make sense. And the scenario where it wouldn't make sense is one that gets thrown back at me every time I give this talk, so often that I made a slide about it, to show you, right? So people will say, I wouldn't want to fly on an aeroplane running any of your software. Okay, fair enough. Okay, there's two types of software running on this plane. There's the software controlling the plane itself, and if I said to you, I could make this software 2.5 times faster, just one failed. Only one. Like hundreds of thousands of test cases, just one failed. So here we are on the Pareto front. There we go. A lot faster. By the way, I also consume less memory. Maybe now your ticket, instead of costing $400, costs $395.95, because I can use a slightly slower chip.
If that test case doesn't fall into the ground at a high velocity.
Yeah, you kind of spotted the flaw in the argument that maybe that test case might have proved to be important. So probably, if the application is safety critical, we might not want to be trading functionality for non-functional properties. Fair enough, but you're not. That's not the only software running on the plane. Here's this businesswoman sitting next to you on the in the bit where you're traveling business class. In the behind the curtain, there's this businesswoman preparing her slides for a talk she's going to give, and it's a long haul flight from London to New York. And she's running a very powerful laptop, and she's doing all these animations, and halfway over the Atlantic Ocean, instead of the plane crashing, because we're using genetic improvement on the plane software, the laptop folds up and the battery runs out, because we're not using genetic improvement on that laptop. If you were in her position, you might be interested in doubling your battery life and having 2 failed test cases. So this solution. So from a correctness point of view, this is twice as bad, right? I failed 2 test cases. But now, all I need to do is just restart the laptop. And for her, in that situation, doubling the battery life could be the difference between working on the slides for 6 hours and working on them for 3 hours. As I say, there's nothing correct about a flat battery. Okay. So there are situations where the correctness of having sufficient resource to do computation can dominate the correctness concern of not crashing, which is considered the archetype of bad functional behavior. If you know that you're going to be regularly saving and you can restart, so then actually crashing is not as bad as running out of battery life. We have got results very recently that show you can improve battery, life. So it's, I don't know if I've got time for this, but I'd really love to tell you about transplantation. Have I got 5 more minutes? Yeah. So another thing we've been playing with is this idea that if you're prepared to accept this world in which software becomes something a little bit more slurpy, kind of liquidy, kind of engineering material where if it passes most of the test cases you're happy, particularly if you can have a mapping between test cases and requirements and know that the test cases that failed were in some requirement you weren't so bothered about, then there's all sorts of things which become possible. And I'm not saying that this is right in every circumstance. I know it goes against received wisdom, but I do think it's potentially exciting because it allows us to have a very engineering view of software. Instead of always requiring that it's a logical construct that's correct by construction, in some sense, which I think is a questionable claim we could make about any software, we have a more engineering view which says we want to make it as good as possible, and we have all these multiple competing trade-offs. And one thing we've been experimenting with in that view, which is covered more detail in this paper, is the idea that we could transplant from one software system to another. In much the same way that surgeons would do organ transplantation, but with hopefully much less mess. And slightly, we get some benefits, as you'll see. So, for example, these applications here might benefit from a great compression algorithm. If we had a library, we have a mechanism for transplanting that in, which is called the code from the library. What if over here you've got something that's got very good compression in it, but it's part of some other system, and you just want to suck out the compression part and insert it into these programs here. There's no library interface to do it. We argue what you need is something a bit like this. We call it Lativa for reasons that escape me. I think it's the initial letters of the approach. But the idea is you have a donor system. Just the analogy with human transplantation doesn't break down, actually. It's quite interesting. You have a host system, and you want to transplant a feature, an organ, if you will, from the donor to the host. So what you have to do, first of all, you have to localize within the system where that particular piece of code is. So we might find some piece of code that's related to the functionality. Then we have to abstract it because clearly the namespace here is not necessarily the namespace here. These might even be different programming languages, although so far we've only experimented with within-language transplantation. But certainly the namespace here has nothing to do with the namespace there. So we'll abstract away the names and get some kind of high-level abstract version of what that code was. Then we need to find a target to insert the code in the host. That's a search problem in itself. We need to make an interface such that we can easily insert candidate organs from the donor into the host and execute them and see if the host accepts them. There's an insertion phase where we essentially have to instantiate those things that we abstracted away with specific host namespace values. They might all be completely wrong, but the idea is that we have this interface and we can take it, as long as this compiles, we can slot it in there and we can run the validation phase, which will have at least 3 aspects to it. Tests that tell us whether the new feature is actually implemented, so does it actually give us any of this new functionality? Regression tests, which are exactly analogous to side effects in organ transplantation. So yes, it might do the new thing, but does it give you any side effects? And quality tests, which test, well, as well as the side effects that affect the functionality of the original program, maybe it also affects the performance. So at least 3 different dimensions, all of which are interesting. So you might get a situation where you have a transplant which gives you the new functionality, but it fails some regression tests. You might still accept that because it might give you a market advantage. It might be, once again, these regression tests you fail in an area of, they map onto requirements that users don't seem to care about too much, whereas the new feature is something they definitely need, and to get market competitive edge, you need it. So you want to suck it out quickly from there, put it in there. In release 2, you'll come along with human programmers and clear up all the mess, but right now, time to market is critical. So you can imagine situations where you fail some of these tests, but you still want to do the transplantation. Just as you would if you're a human and you get a liver transplant and it has some side effects, but it's still better than not having a liver. So the nice thing is, unlike human transplantation, which is a bit of a kind of a one-shot, play and pray kind of scenario, we have the ability to repeat this over and over. So we can put this all in a nice software engineering, completely automated environment once we have those test cases, and try hundreds of thousands of transplants, making this a search problem so that we hopefully guide the transplantation, it's not completely blind, until we find good transplantations. So I just want to give you an overview of what we've managed with this kind of approach so far. So the overall strategy is to take code, treat it as an engineering material. We call it genetic improvement. The idea is that the code of your program is just like genetic material. It can be chopped around and done silly things with. And instead of correctness, we're after faithfulness with respect to some test suite. And the sorts of things we've been able to do is we take a program called Bowtie 2, which is about 50,000 lines of C, C++. We have as our fitness the non-functional property of interest and some test cases. In this case, non-functional property is execution time. We have a whole bunch of test data. And our approach is only as good as the test data. So if you have lousy testing, then we'll produce programs which are lousy. Okay? No, we don't square that circle for you. But guess what? All the software you're using this afternoon is, subject to pretty much the same kind of correctness criteria. I hate to be the one to spoil the belief in software, but I don't know of anybody who's using any software these days that's been verified completely correct. Certainly not in a university environment. So we're all using software that's only good as the test data anyway. It's my argument. And we've produced from that multiple versions of this program Bowtie that are improved. Now this program does it does gene sequencing, and these algorithms can be very slow. So we managed to improve the time. The take-home message: we managed to get this program 70 times faster on human genomes. It's an open source program designed for arbitrary genomes. We have a held-out set and a training set, and with the training set using these genomes as test cases, we can produce a version that's 70 times faster. That's 30 different interventions into the code. But after a hill climbing phase to clean those up, so we just selectively remove them if they don't produce more than 1% improvement in execution time, we end up with only 7. So 7 places where we intervene in that program can produce a 70-fold increase in performance for this particular task problem, human genomes. So what some referees have said to us, mercifully not the editor was kind and didn't spend all the time listening to those referees, was, well, you know, you just make 7 changes to the software, it's not that exciting, you know. But actually, all the magic here is in finding the right 7 changes. Yes, you can be making 7 random changes to that program till hell freezes over and you won't produce any improvement. What all this machinery gets is it finds the right 7 changes which can make a dramatic speed up. And the other thing is, for this particular problem, there's a thing called the Smith-Waterman test, which allows us to check whether the genome's matches it produces are good quality. And it actually produces a slight improvement in quality as well. So I'll run through this very quickly just to give you an overview. So we've also used it to improve CUDA architecture within its. So CUDA is a language for NVIDIA cards, and we managed to improve the performance of those. And the thing we were able to do here was make it 7 times faster. But the deal was this: NVIDIA bring out new hardware all the time. The old software runs faster on the new hardware because the new hardware is faster. It's got more processors. But it could run even faster still if it was optimized for the new hardware. But the stuff's coming out so fast, programmers haven't got time to keep up. Using our approach, we can automatically update the old software for the new hardware so that you get the extra. So this 7 times faster is 7 times on top of what the hardware is already giving you. So it's a kind of automated updating approach. And we've also taken the Minisat SAT solver and used it to achieve a kind of specialization, a bit like a GP version of partial evaluation, if you will. And that produced a version which was 17% faster. Doesn't sound that exciting, but this is something that's been optimized to death by humans. In fact, we took versions of Minisat that had been submitted to a competition for humans to optimize. And so that allowed us to make a claim that this algorithm is finding programs which are better for particular tasks than human-optimized versions. And finally, just to run through real current stuff we're working on, some things which have only just been accepted a couple of days ago. We're looking at this, the thing I talked about with the transplantation has now been implemented, and there is a tool that you can use that's actually quite scalable. I'm really excited about this. We have transplantation technology, and it works. You know, it transplants real functions from real systems into other ones. It doesn't always work, but I mean, it works sufficiently often that it's interesting. We're able to trade memory and speed. So you've got a Pareto front where you can see how much dynamic memory you consume and how fast your system is. That's quite interesting, I think. That's only benchmarked on relatively small unit size code, a few thousand lines. We've got specialization, that kind of repetitive with the Minisat. We've shown that works for many downstream applications, including software verification, in fact, which is another downstream application of SAT solving. And we've managed to take a bite out of this energy consumption problem, but I have to be honest about that. There's still a hell of a long way to go there. And one of the things that's also turned out to be quite exciting is we can grow small pieces of functionality in isolation, which on their own would just be toy code, but then graft them into existing real-world systems such that they become something more than toy code when grafted into the real-world system. So we've got a thing that does language translation using Google Translate. It's trivial on its own, it's just a few lines of code, 10 lines of code. But when transplanted into an instant messaging system, it gives you the ability to have multilingual translation in real time as you're messaging. And we don't know how this 200,000 line program works, but our algorithm can find a way to grow and graft this extra functionality into it without having to know. And we're hoping that this particular program is going to have some real users. So far this is all laboratory stuff, but we want to try and deploy some of this code into the real world and get people using it and see if they do find it any good compared to human-generated code. So in conclusion then, I think that engineering really is optimization. That's what engineering is all about. And search-based optimization is software itself. All the optimization elements are software. So software is kind of ideal for search-based optimization because it's almost like you can insert the solution into the solution and get adaptivity. And in next steps, I've talked a little bit about coevolution and some possible ways in which we could actually optimize the code itself through transplantation, genetic improvement, specialization. Thanks very much for your time. It is now 1 minute to 4, so if people have other commitments, go, and if you want to stay and ask questions, just stay.
So I just want to get an idea, so how long it actually takes for this automatic improvement for the algorithm, for the code itself?
Very good question.
Roughly, how
long do you have to wait for
the
this stuff? Yeah.
How do you
So on a standard desktop, the thing that optimized Minisat takes 26 hours.
Okay.
So it's a non-trivial amount of time. It's not something you're going to happen with a press of a button, but if you think about the thing it's doing, it's producing a new version of the software that's specialized for your downstream application that makes it faster. So you do it once, you get your new version, off you go. So it's 26 hours, and that is on a standard desktop, so we could make it faster. The bow tie one, I think, similar. It's either days or hours, you know, it's that kind of ballpark. None of this happens in a touch of a button. I have done a talk at Seams, a keynote, where we talk about how we might get this to be online, but not by just taking the algorithm and plugging it straight into the code, because you know, if I'm using this and I go to a new area of bandwidth, oh, bandwidth's gone down, I want the algorithm to find me a better version, right? And a 26-hour wait, that's not going to be a good solution. But what we hypothesize is something we call like dreaming iPhones, where overnight it's charging. In the day, it's recording a little bit of what's going on. And then overnight, it's replaying those and trying to work out the optimization for tomorrow, if you see what I mean. So when you look at it, it'd be as if it was dreaming, where it could be rerunning scenarios and trying different modifications to the code. And then the next day, those are all there preloaded, ready to deploy like Band-Aids when you move into a different, you know. But trying to do it in real time is not a win at the moment. You know. But many devices have this two-phase, you know, use phase, idle phase. So even offline with subsequent online deployment of solutions can, I think, be quite attractive. It was a good question.
Okay. So okay. So possibly naive question: how does documentation keep up with this notion of transfer?
That's not naive. That's an excellent question. So another kickback I get from software engineers is, I might believe it passes all the test cases, and I might be happy with the improvements. But if I can't maintain it as a human, then I still can't have that. I'm sorry, you know, because a lot of companies have done outsourcing and they get this code back, and it's all better and everything, and passes testing. But then they still find they have problems because they can't. Their in-house people can't maintain it. The interesting question to ask as a researcher is, if we automatically generated the documentation, would it be better or worse than documentation generated by human programmers? So our system is doing these changes to the system, to your software. We know it's actually only going to make few interventions often, and they're going to have dramatic improvement. If it came with an automated explanation of those changes, the documentation might not read like poetry. It might lack a few expletives you see in human documentation. It might, I mean, maybe we could generate those too, I don't know. But my point is, human documentation is not actually that good. Maybe automated documentation that explains why this change made the software better, which might in some cases be, look it up as a template or it's this. So one of the changes we find very obvious is switching off loops. Loops that don't matter, switch them off. And the algorithm finds those very quickly. So that's a very easy explanation, right? This loop didn't seem to matter, we switched it off. It still passes all these test cases. If you doubt that, then give me some new test cases, you know. But other ones are a bit more subtle, like I pass this parameter into this function, it gets a lot faster. And I don't really know what the function does, and I certainly can't expect the algorithm to discover that. But we haven't started, we're just starting to think about how we could automate that documentation by hypothecating a bunch of experiments that the improving algorithm could then run in order to try and generate documentation to explain why it worked. So we might give the human a prioritized bunch of interventions where the top one is the best explained one. And as you go down the list, we get more and more probabilistic in our explanations of why this seems to work. And the human can choose, you know, can say, okay, well, I'm not going to bother going, you know, I feel fishy here, so I stop, you know, and then I don't get the speed up I could get, but I still get some, and I'm happy, you know, you see where I'm going with that, you know. It's quite an interesting problem to think about which experiments you could automatically run to explain why it is that passing a particular parameter to a function makes it faster, without understanding what the function does. There's still quite a lot of documentation you could produce, I think, that would help the human, particularly if they know the system, go, ah, I get it, I see what's going on there. Yeah, you know, it only needs to be 8-bit, or you don't need the parity check in this case, or whatever.
Okay, yeah, it's an interesting answer. I was expecting more of an answer in terms of perhaps transplanting the documentation as well, performed by the humans. It's interesting that you dismissed
That would be a
completely.
much more challenging task than transplanting the code. Because if we transplant the documentation and then have to get into all the natural language processing and then try and update the documentation, and the documentation may not have been correct in the original anyway.
Yeah, you need
Good luck
you
with
need to
that.
abstract the documentation as well, yeah.
Abstract, yeah, but what if the documentation is, particularly if it's just comments we're talking about here, they're notoriously out of date and wrong anyway. We might be compounding that, whereas if we generated new documentation, that's everything we say is guaranteed to be correct. I mean, imagine reading documentation like that. You've never done that before, right? Yes.
I'm interested in the question, let's say, let's take the case of genetic algorithms. So there is a disparity between, so the key, I think, to success of such algorithms is the representation.
Yes, that's one
So
way, yeah.
the fitness function, the domain is the software. So it's the software you submit to test. But when then you, let's say, make a mutation and crossover, you do it in another space, it's representation space, and that could be completely non-monotonic. So the relationship between small operations in GA can have dramatic effect on fitness, and vice versa. And in the big spaces, it's absolutely this effect can be. You have absolutely no way of finding the optimum, for example, or you can have very nice monotonic increase. And finding this right representations is important, especially if you often assume that there are, for example, this program is a collection of independent components that you can replace. So the question is really how to find this right representations. Once you find them, of course, the GA can work.
You're absolutely right.
So
This is an enormous problem, and if I'm completely honest with you, I think that what our current algorithms achieve could be characterized perhaps slightly pejoratively as relatively randomly discovering good small changes and then composing them in a greedy way, which isn't tremendously intelligent from a search-based optimization point of view. And the representation is an issue in two ways. One is the way you said, but the other way is that in standard GP you represent your problem as a syntax tree. It's the natural representation for a program as a computer scientist. But the trouble is we're making relatively small changes to large syntax trees, and we've got a population of them, maybe hundreds. So we get a space problem if we use that representation. So actually the representation most commonly used is a sequence of edits. And so now your representation is very like near neighbours in that space, things with a small Levenshtein distance from each other, have an even more dramatic effect in the sense that they're not even small changes to the syntax necessarily, or they're not kind of necessarily proximate changes to the syntax. So lots of locality and near neighbourliness is lost. And I think that combined with the fact that our fitness function is often just measuring the number of past test cases in order to do functionality, rather than some more fine-grained measure, are two big open problems that need to be addressed. If we could find a much better representation where we know that a near neighbour is semantically near, so these programs that I've moved to by mutations are semantically similar in such a way that I might get a more smooth fitness function. But then each fitness function imposes a different search space. So if I've got these multiple, here's energy and here's test cases, each one of them is it's very different. So what's smooth for one might be very jagged for another. It's a very thorny problem. On the plus side, if I just finish up there, on the plus side, we've managed to get tremendous results with relatively naive and simple algorithms. So just imagine what you could do if you could have a better fitness representation and a better problem representation as well.
But that's just a question, because from a theoretical point of view, because the understanding of evolution in biology, for example, genetic codes are adaptive as well. So they're actually evolving constantly. So
yes.
which genes map to which proteins, for example, is different between, let's say, mice and human. We have expression of the same gene different in mice. And that means basically the mapping from the letters and then the words to which software it translates to. So the mapping, and so I'm wondering if there, because that's obviously such a big area, so many works there, maybe somebody have started looking at the evolution of the code.
In the genetic algorithms community in general, there's lots of work on that, as I'm sure you know, so adaptive fitness operators, adaptive crossover and so on, changing the...
No. This is controlling the parameters. I'm talking about the actual alphabet and, let's say, how many letters and which letters translate to which features of basically encoding, decoding problem. So given the software, which string it translates to?
So what I was going to go on to say is no one's even done what I was just... what I misunderstood as your question. No one's done that with SPSE. Never mind anything where you're actually changing the representation. I think, are you talking about the mapping between the genotype and the phenotype here?
Yeah.
So
adaptive mapping between the genotype and
so that's, to my knowledge, that's not been tried in any of these genetic improvement problems. But what also hasn't been tried, which I know has been tried for other problems, is just more, perhaps less radical, what we might call learning as we go along. There has been, very recently, we've experimented with this thing called hyperheuristics, where we're not actually learning the phenotype-genotype mapping, but what we're learning is the low-level operators to apply. So whereas traditionally you might have parameters that say how often you rotate, how often you cross over, where you cross over, and then you might try and learn those as you go. In hyperheuristics, you try and actually learn the particular mutation operators to apply. And we have done some work with that, but that's still not approaching what you're talking about.
Well, I did work in this area. It's called optimal parameter control. So there are parameter also control mutation operators, but that's
So do you view this mapping as just another parameter?
Yeah, that will only work under the condition that you have monotonic mapping between representation and fitness. It will not work if there's monotonic. I mean, it will do nothing.
What if it's almost monotonic, but every now and then it goes down a bit? Surely, as long as the general trend is up. Like if you had a high Spearman rank correlation, but it's non-monotonic, I would have thought it would still work.
We should talk about it at some point.
Yeah.
But it is the latest evidence from evolution from biology suggests that our genetic codes are constantly adapting. The representation between phenotype and genotype is not a fixed thing. And it's adapting depending on whether the fitness is monotonic with respect to mutations. Whether small changes in genetic code correspond to small changes in fitness. If they're not, then the genetic code changes.
And one of the things that's interesting in doing research in this area is that we're doing research on the application of computational research to software engineering. And software engineering problems are changing all the time. New areas coming up, and app stores and new, the whole problem of cloud optimization has come up in the last 5 or 6 years. And I'm sure if I give it sort of 5 years' time, there'll be some other new thing that none of us have even. But at the same time, there's a very strong community developing new optimization algorithms in general, and the two things, you know, kind of feed into each other. Although most of the feeding is perhaps it's going this way rather than that way. But I still have a long-term hope that before I finish my career, there will be some kickback from the software engineering community into the optimization algorithms community. But there's only been very small. So as these new, and then that community is also loosely coupled, as you say, to the sort of biological, you know, the real wet evolution. People actually look at evolution for the real, you know, and that feeds in inspiration. So I must say, sometimes this whole idea of nature inspired can get a little bit trite. You must have experienced this too. Like the number of times I've read about bizarre algorithms that are alleged to be inspired by nature, just almost for the sake of it. You know, like look out the window, spot an arbitrary thing. You know. Blue tit algorithm, right? And then off you go, you've got to pay for it.
A new model of computation.
Sorry?
Sorry. A new model of computation inspired by biology.
You mentioned that in the long list of areas that have been approached with SPSE, you mentioned verification, which is kind of close to what I do. Can you give examples of
Yes.
kinds of things?
Yes, so one of the, if as long as you count model checking, so model checking, there'll always be this from that above a certain size of number of states, no matter how much cleverness you put in, there'll be systems that are beyond our reach to model check. But in those situations, of course, we can still